Hello again. In this video, we're going to go over section 2.6, part 6, which is about Theorem 213 on the continuity of functions with roots. And so the theorem says assume n is a positive integer. If n is an odd integer, then f of x raised to the 1 over n power is continuous at all points at which f is continuous. And if n is even, then f of x raised to the 1 over n power is continuous at all points a at which f is continuous and f of a is greater than 0. So to illustrate this theorem, let's look at example 7. And in example 7, we're supposed to find all the values of x where the following functions are continuous. And we're going to start with part A, and then afterwards we'll look at part B. Okay, so let's look at part A first. So the first thing here is notice that this function can be written in terms of exponents. And instead of writing it as a square root, you can write it as 9 minus x squared raised to the 1/2 power. And then n is even in this case, right? N is equal to 2. So in the theorem it said if n is even, then this function f of x raised to the 1 over n power is continuous at all points a at which f is continuous and f of a is greater than 0. So we need to, if we're going to determine where this function is continuous, we need to look at f of x, which is the inside function here. Okay, and so in this case, the inside function would be 9 minus x squared. So that's our f of x, right? And so we need to see where this is continuous, right? Where f is continuous, and where it's positive. Okay, so where's this function continuous? Well, it's a polynomial, so it's continuous everywhere. Okay, and we also need to make sure that the function's positive. Okay, so I'm going to figure out when this function's positive. So let's take this and set it greater than or equal to 0, and find out what x values make that true. Okay, so what we're going to do here is factor this. Now this factors into 3 plus x times 3 minus x. And it would be useful to find out when this is actually equal to 0. So I'm going to set it equal to 0 just for a moment, and then solve for this. And I think you can see it's 0 when x is equal to -3. And if you add x to the other side, when x is positive 3. Okay, now that's important because what we're going to do is we're going to create a sign chart where we break up the number line at these points. So the first interval is going to be from -∞ to -3, and then we're going to go from -3 to 3, and then 3 to infinity. Okay, I'm going to leave myself a little bit of room over here. And what we're going to do is we're going to pick test points in these intervals and plug them into this function and see whether we get a positive value or a negative value. Okay, so I'm just going to write that function down here as a reminder. And we'll pick some test points. Okay, so it doesn't matter what point you pick in this interval. Just pick a test point. So I'm going to pick like -4. And when I plug it into here, I think you can see I get 3 minus 4, so I get -1. And then I get 3 minus a -4. Okay, which of course is 7, 3 plus 4, right? So you get -7 overall. Okay, and so that indicates that for any point that you pick in here, you're going to get a negative number out when you plug it into this function. Okay, so that means that this is not a solution to this inequality. Okay, so let's pick a test point in this interval, like 0. And when you plug 0 into here, you get 3 times 3, right? Which is 9. And so every point in this interval would satisfy this inequality, right? And then I'll just pick a test point in here like 4, and when I plug that into this function, I get 7 minus 1, which is -7, okay? And so that means this is not a solution, right? This interval does not is not a solution for this inequality. Okay, so this appears to be the solution to this inequality. Now, that says, now according to this theorem, this function, g of x, is continuous at all points where f is continuous. Okay, and remember, f is continuous everywhere. And at the points where this function is positive. But this function is positive only on this interval. Okay? Okay, so that means this function g of x is continuous on this interval. Now we do need to check the endpoints, because if you remember, continuity on an interval when you have endpoints is determined by whether it's left or right continuous at the endpoints. And so I'm going to check this. We're not really sure if we need to include the endpoints yet. Okay, so in terms of continuity, we're not quite done, but f of x is positive on this interval. Okay, but we are going to check the points, the endpoints, to see whether it's continuous at the endpoints. Okay, so to do that, I'm actually just going to look at the graph of this function. If you were to graph this square root function that we have, the square root of 9 minus x squared, the graph of it looks like this. And so we're just going to check and see whether it's continuous at this endpoint. Okay, so we need to check left continuity, or rather right continuity here. So the limit as you approach, as x approaches -3 from the positive side, right, from the right side. I think you can see as it's approaching -3 from the right-hand side, the y value is getting closer to 0. Okay, and that needs to be equal to g evaluated at -3. All right, well, when I plug a -3 into this function, I get 9 minus 9, so I get 0. Okay, and so it is right continuous here. Okay, now is it continuous from the left side? Okay, and that's written up here. Okay, in terms of notation, this limit as you approach I don't know if I said positive or -3, but it's -3, right? But you're approaching -3 from the positive side. And I think you can see as you approach from the positive side, right, the limit is 0, which happens to be the same as g evaluated at -3. Okay, and so that shows that it is right continuous. So you do need to include -3. Okay, now let's check left continuity over here. So we're going to take the limit as x approaches 3 from the negative side of 3 and see what that limit is. And I think you can see that it's equal to 0, right, from this graph. The y value is getting closer to 0. And then that needs to be the same as g of 3. And when you plug a 3 into this function, you do get 0. And so that shows that it's left continuous at 3. And so in terms of continuity, it's actually continuous on the closed interval from -3 to 3. You need to include these endpoints. Okay. Okay, so that's kind of an application of the second part of this theorem. All right, now let's look at part B. Let's try to figure out where this function is continuous. Okay, now notice in this case, it's being raised to the 2/3 power. And you can write that in this form, right? That's the same as saying this to the 1/3 power and then raising that to the second power, because you multiply exponents in this case, okay? So we're just going to rewrite the function like this. They're equal, okay? And the reason we're doing that is because this inner piece right here, we're going to apply that to the theorem. And notice that this 1 over n, right, n is equal to 3, so it's odd, okay? And so according to the theorem, if n is odd, then this f of x raised to the 1 over n power is continuous at all points at which f is continuous, where f is this inner function. Okay, so according to the theorem, this function here is continuous at all points where this inner function is continuous, because this is an odd power here, right? 1/3. Okay, so where is x squared minus 2x plus 4 continuous? Well, that's a polynomial, so it's continuous everywhere, and therefore this entire function is continuous everywhere. Okay, so f is continuous for all x values according to the theorem. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.